All right, thank you, Shoshana. Thank you, everybody. We are really thankful to be given the opportunity to study this Mercury Lander mission concept, and really excited to show everybody what we've put together so far. It's not me alone. It's me leading a team of really engaged scientists, which are listed here from many institutions, as well as a great engineering team headed out of APL by Sanai Kabuta. And I could not have done any of this without their help and contributions. So let me give a quick recap on the spacecraft reconnaissance of Mercury. And I don't need many slides for this because there has not been many missions there. The Mariner 10 mission was launched by NASA in 1973 and performed 3 flybys of Mercury in the mid-70s. All 3 of those flybys saw the same side of Mercury's surface in sunlight due to the spin-orbit resonance of the planet and the orbit of the spacecraft. So we saw just under half of the planet and sent nothing else for many decades after that. I think a lot of people kind of falsely equated Mercury to being basically just like the moon after that because of its heavily cratered surface. About 40 years afterwards, NASA sent the Messenger spacecraft, which was a discovery mission. It launched in 2004 and performed 3 flybys of Mercury on its way into orbit in 2011, and it spent 4 years in orbit about the innermost planet. It had a broad suite of instruments, and it really, rewrote the book both figuratively and literally about Mercury. There were many findings that were surprising to people, including some that made any of the leading hypotheses for how the planet formed incorrect. And it's always exciting and frustrating to have all of your theories kind of thrown out the window. But now we have new data that lets us revisit how the innermost planet may have formed. The Bepi-Colombo mission is a joint ESA-JAXA mission, which was launched in 2018. It just performed a flyby of Earth earlier this last month, and will perform several flybys of Mercury before it enters orbit in 2025. So following the often used mantra of NASA, the way you examine a planetary body would be first to fly by, we've done that, then second to orbit, we have done that, and the next logical step to get more science answers is to land. And a lander on Mercury is also the consensus of the Mercury community as the next step in Mercury exploration. There was a decadal study performed a decade ago now for the last decadal, and it was a limited study. It was finished in 2010, which you may know is before Messenger went into orbit about Mercury. And the conclusion of that study was that it was too challenging and expensive for a New Frontiers mission at that time for that decade. Since that time, there have been significant advances that make it really compelling and important to perform a new study for this new decade. And among those advances include, of course, we have messenger orbital observations that help us to better tailor the scientific questions we want answered and the means by which we answer them. Technology, of course, has advanced, as well as capability like launch vehicles, solar panels, and solar electric propulsion, and other things like that. And then, of course, changes to the New Frontiers costing. So, for example, phase E and F are not under the cost cap anymore, nor is the launch vehicle, and they were in the last decade. So why should we land on Mercury? Well, as I alluded to before, Messenger revealed surprises about Mercury, including its highly chemically reduced and unexpectedly volatile rich composition. This is unique among the terrestrial planets, including the moon. And like I said before, it's unlike any of the predictions that had been previously proposed for the origin of the planet. We really need to measure the surface in situ in order to answer kind of the next level of science questions to better understand the mineralogy, especially, and geochemistry of the surface, to better constrain the interior structure, to measure the active and the remnant magnetic fields at the surface, to look at the interplay between the processes that alter the surface and make its exosphere, and then also to provide ground truth for the Messenger and Bepi-Colombo data sets. The landed observations will only be one spot, and so we need to put that into context of the globe. So as an end member of terrestrial planet formation, Mercury really holds unique clues about the distribution of elements in the earliest stages of the solar system, and not only will tell us something about the formation of our own solar system, but can also tell us something about how exoplanets may form and evolve when they are formed really close to their host stars. So I alluded to our science team before. Here's a picture of our Zoom meeting during our engineering run of much of the team. It was split up into 4 major discipline groups: geochemistry, geophysics, Mercury environment, and geology, with a scientist set to head each one of those. We also had Sebastian Bess as a representative from ESA, for Bepi Colombo, and a couple of other experts that went before, during, and after the inception of the Messenger mission. Nancy Chabot was my deputy PI, and Rachel Klimo was my project scientist, and they were really important in getting this study moving and done. We had monthly science team telecons in order to develop the traceability matrix and payload options. We put quite a lot of effort into thinking about what the payload would be. We had our engineering run the last week of March, which was the first all virtual engineering design run in APL's history. And now we're honing in on and completing the engineering development, and of course, preparing that final report. So we came up with 4 major science goals for this landed mission, each going along with those discipline groups I had mentioned. And I will go into those in detail individually here. So goal 1 was a geochemistry goal. It was to investigate the highly chemically reduced and unexpectedly volatile rich mineralogy and chemistry of Mercury's oldest terrain to understand the earliest evolution of this end member of rocky planet formation. So what is shown here is a map of Mercury, and the areas shown in blue represent terrain that was termed the low reflectance material, or LRM. This material was discovered by studies done on messenger data, and it is often associated with exposure from depth and with the oldest terrains on Mercury. And one of the hypotheses is that this is representing a graphite flotation crust, which you can see on the right there, that formed out of a magma ocean and then subsequently was covered over by extensive volcanism, and then would have been impact gardened into the surface. And so if we can figure out more about this LRM terrain, then we will learn perhaps more about the very earliest crust, maybe primary crust of Mercury, most of which is no longer visible. We have 3 science objectives associated with a couple of instruments. One is to determine the major and minor elemental composition of the LRM. So from orbit and messenger, we have gamma ray spectrometer data of many of the major elements, but landed observations will not only give us a very specific composition of one single terrain, but it will also allow us to get better precision measurements on the major and measurements at all of the minor elements. The second objective is to determine the mineralogy of that terrain. That's something that we really don't have a good handle on from orbit. A lot of information on mineralogy often will come from near-infrared spectrometry, and the spectra of Mercury are extremely flat because there's just no metallic or iron in the surface, no iron in the minerals of the surface to give us those diagnostic absorption bands that you would see on the moon. And then the third objective is to see how heterogeneous the surface is. Obviously, we are not landing in multiple locations, so we're limited to measurements around the lander, but we will do that by performing the mineralogy measurements at 2 of the landed legs. So the major instrument doing the mineralogy is an X-ray diffractimeter / X-ray fluorescence instrument, like the Chemin instrument on MSL. And the sample will be brought to the instrument via 2 PlanetVac samplers. These are the same samplers that Julie Castillo was using on her series study as well. Goal 2 is a geophysics goal to investigate Mercury's interior structure and magnetic field, to unravel the planet's differentiation and evolutionary history, and to understand magnetic fields at the surface. So the 2 figures here show a couple aspects of this. The one on the left is showing a schematic of the interior structure of Mercury, which of course has an abnormally large core to full radius. And we have some information about that structure from orbit and from radio science, but we can get more refined information about that, especially about the size of the core, from landed measurements. On the right is shown a map of some crustal magnetization discovered by MESSENGER. So this is a remnant magnetization from billions of years ago at the time when this volcanism was solidifying on the surface. And having a measurement on the surface will help us better understand that magnetization, what minerals are holding that magnetization, and also time resolved measurements of the magnetic field at a specific spot on the surface. And so that is basically the objectives I just went through. One is looking more at the interior, and to do that, we'll use both radio science, which will give very precise measurements since it's a stationary platform on the surface, as well as a gravitational accelerometer used to not as in-depth as something like InSight, but to make some measurements that will be able to tell us more about the size of the core. And then to measure the magnetic fields, we have a magnetometer on a boom on the lander. And again, the mineralogy information we'll get from goal 1 will feed into what elements might be holding that ancient magnetic signature. Goal 3 goes along with the Mercury environment. We want to investigate the active processes that produce Mercury's exosphere and alter its surface to understand planetary processes on rocky, airless bodies, including the moon. So there are many things bombarding the surface of Mercury. There's photons, alpha particles, there's dust particles, all sorts of things. And that not only will act to weather the surface, but it will also produce the tenuous exosphere of Mercury. And so some of those processes can be seen here in this diagram. We have a suite of instruments that can address looking at this science goal. So one is to take a look at the neutral exosphere, which would be done with a neutral mass spectrometer. The second objective is to look at the fluxes of charged particles, which is done with an ion mass spectrometer and an energetic particle spectrometer. Third is to look at the influx of micrometeoroids using a dust detector. Fourth is to investigate the nature of Mercury's regolith, and that will be performed with 2 cameras mounted on lander feet and paired with some color LEDs to get information both in the dark and minor spectral information. And then to the best that we can investigate characteristics of space weathering. When we take subsequent samples with a planet vac, you're sampling slightly more deeper samples with every turn. And so do we see a difference with depth? And then finally, goal 4 is a geology goal to characterize the landing site in order to understand the processes that have shaped its evolution, place the in situ orbital measurements, place the in situ measurements in context with the orbital, and enable ground truth for global interpretations of Mercury. Again, we will have information on one spot on Mercury, but so in order to make that more generalized for the planet, we need to link those to the orbital data, which we have globally. And I like this image down here because it shows that of the 4 terrestrial planets plus the moon, we have in situ pictures of each of them except for Mercury, so we don't know what that will look like yet. For this goal, we have objectives, again, to connect the orbital information to the ground. We need context and really need to know what the landing site is like, so we'll be taking images on descent. That's both for science and for the landing. And so we'll have a descent cameras. We have camera up on, it's on the high gain antenna used to take panoramas and get the context of the landing site. That also can be paired with LEDs. And again, we want to link these to all of the other instruments and the orbital. All right, we explored 4 major categories of trajectories in order to get us to Mercury. We had a fully ballistic scenario. We had a ballistic interplanetary cruise with a solar electric propulsion or SEP spiral. We had a fully SEP version And then the one that we ended up going with is an SEP interplanetary cruise, followed by a chemical orbit lowering phase. And so that arrives with a C3 of 0 to reduce the costs of orbital insertion. And then by lowering with the chemical thrusters, we avoid having to sit at Mercury for a really long time before landing. And the launch vehicle we ended up with was the fully expendable Falcon Heavy, and that launch capacity of that vehicle really enables this mission concept. So where to land? So you could design a mission to Mercury to land in a number of places that would be scientifically compelling. In order to do the study, we had to pick one. And due to the compelling nature of this low reflectance material and what it might tell us about the very early history of Mercury's evolution and differentiation, we chose to target the LRM as our landing site. So what we're going with for this study is positioned kind of right in the middle of the graph down here, and I'll zoom in a second. So this is kind of the geological context of this area. It's around 40 south, 170 east. It's within a regional exposure of this low reflectance material. This material is really distributed everywhere here. It's not making up 100% of the terrain here, but it's basically everywhere. So if you landed somewhere in here, you should be able to get components that have this LRM inside of it. The terrain type is called intercrater plains, and it's one of the oldest surfaces on Mercury. And so you can see all the way to the right, kind of the broader context of the terrain in which we would be landing. Mission timeline, we would launch in March of 2035. We would perform 1 Earth flyby, followed by 2 Venus flybys, and then 5 Mercury flybys over the course of the next several years. This is a trajectory similar to what Bepi Colombo is doing now, minus a Mercury flyby. Mercury orbit insertion is in January of 2045. So if anybody has kids that want to work on this mission, get them involved soon, and they could be the PI in 2045, who knows. We'll have an apoherm lowering event a couple of months after orbital insertion with a landing of April 12th, 2045. Obviously, this is just a specific scenario to make the mission study close, and the timeline could be changed forward or backward. There are a lot of opportunities to get to Mercury since we're so close. Surface ops would end after almost 3 months in mid-July of 2045. The spacecraft is a 4-stage spacecraft. On the left, you can see what it would look like stacked inside of the fairing. The cross dimension there is nearly 5 meters. And on the right, you can see the 4 different stages. On the bottom is the cruise stage, which is again an SEP stage, and that's why there are giant solar panels that would be deployed. The second to the bottom stage is the Mercury orbit insertion stage, followed by the descent stage, and then on top of the whole assembly there is the lander, which I will show in detail in a moment. So the lander is a 3-legged lander. A few of the components are shown there. You can see the scale bar of 3 meters down there to the right. On the 2 legs closest to the left side of the slide would be mounted planet backs, and that's what would get the sample into the XRD XRF for measurements. That big green thing sticking out of the side is the power source. We are going with an RTG because, as you will see in a couple of slides, most of our operations will be performed in the dark. We started with a very robust science payload, which is listed here and which I went through before, fully expecting that we would encounter some hard trades down the line when we ran into mass and costing problems. And we're happy to say that we actually didn't have to get to those hard trades, and could end up with a really robust science payload for a lander. In addition to the official instruments, there's also, again, the 2 planet backs, radio science, and there is a LiDAR, which would be used for the landing phase of the mission. So here's a diagram of what would happen at landing. First, you would finish a slew and start a burn, get a star tracker fix, and then where that red dot starts here, you begin the solid rocker motor braking burn. Time before landing here is just over 2 minutes at an altitude of 20 kilometers, and then you're going basically at the orbital velocity of about 3.4 kilometers per second. Once the solid rocket motor burns out, just over a minute later, you're down to an altitude of 6.6 kilometers, and you have significantly slowed down to a velocity of about 83 meters per second. At this point, you're doing a brief coast, and you're going to change to a different attitude for the liquid burn. At this point, the hazard detection of the spacecraft is starting, so we will not have a fully vetted landing site going into this process. There's not sufficiently high resolution images from Messenger, nor will there be from Bepi-Colombo. In order to pick a pinpointed spot, we will have a camera on the orbital stage that can do some reconnaissance at a maximum pixel scale of about 1 meter, which will give you a good idea of the hazards, but not enough to know all of the hazards at the scale that the spacecraft needs to land. And so there will be autonomous hazard detection happening on landing using descent images and a Lidar. About 34 seconds before landing is when you start the final approach with liquid propulsion. That's an altitude of about 3 kilometers. And then right above the ground, the engines will shut off. And at the bottom there, it's showing a kind of a cartoon of the landing error relative to the hazard map that will be obtained. We will have 1 full Mercury year of surface operations. And so this is a busy chart, but I'm going to walk you through it. It's a lot of given information here. Mercury is so close to the sun that it not only gets very hot for any incoming sunlight, but the reflected light off of Mercury is also causes tremendous heat on any kind of landed instrument, on any kind of spacecraft, in fact. And so because of that, we will land very close to dusk. And so the landing time of April 12th for this scenario is just before dusk. We would land, so you have images of where you're landing, also the LiDAR. Upon landing, you would immediately take context images with the panoramic camera and with the lander leg cameras, because pretty soon you will be in the dark. The Mercury environment instruments, which are shown up here, would start taking data right away and basically operate continuously throughout the mission, which is great because then you can get a lot of data over time from one position on the surface. The geophysics instruments, likewise, will mostly be operating continuously throughout the mission. The radio science will have a gap in the middle as we lose communications with the Earth for the middle period of time. The geochemical instruments, the GRS has to cool down, and so we'll wait a little while before operating continuously. And then we have some measurements with the planet vac scooping sucking the material up into the XRD and taking a number of measurements over time here from 2 different sites on the surface. And again, we'll have a flurry of images taken right away while there's still some light, and then periodic images using pretty much LEDs throughout most of the mission. There is going to be some experimentation with whether or not we could use the, for lack of a better word, air glow of the sodium exosphere and a long exposure to do some imaging as well. And then we would pick up and kind of do some frantic imaging near the end until the lander dies. So going back up to the top line here, we land just before dusk. We operate in the night while we have direct to Earth communications for just under a month. Then we lose direct to Earth communications for a period of time here, just over a month. And then we regain it at the end for, again, just under a month until the very end. And the end of the spacecraft is limited by the thermal environment that is experienced when the sun starts to come back up. The amount of data acquired is just under 11 gigabytes of data. We will prioritize certain data coming back first, just in the event that you cannot pick up the lander after the Earth communications cuts out. We fully expect that the lander would last through the night thermally, and of course with the RPS, the power shouldn't be a problem through that time. But we'll have a period of good downlink at the beginning, and then we'll have to just store the data on the recorder for this month plus, and then we'll do a big download right when we come back into Earth communications, and then just keep taking measurements as long as we can before the thermal environment gets to the spacecraft and the mission is over. Cost is always something that gets refined over the course of the study and kind of oscillates up and down as things get refined. So we're not quite done oscillating, but we are honing in on a number. And the kind of exciting thing here for me is that even with our 11-item super robust payload of science instruments, the latest cost numbers are just above the New Frontiers cost cap in fiscal year $25. The spacecraft costs themselves, which are the big green area and a bulk of the costs, are actually undergoing another iteration and are expected to come down a little bit. But it was really exciting to see this very robust payload come in basically right around the New Frontiers cost cap, because the previous decadal study was coming in way above that cost cap, and even with a pared down, pretty lean payload, was still above that cost cap. And so to have our super ambitious payload coming in right there where we're still oscillating kind of around that line was really exciting. By removing 4 of the more expensive instruments, the GRS, the accelerometer, the neutral mass spectrometer, and the dust detector, this can be brought down to basically at the cost cap. And again, we're really oscillating around this cost cap. And so this is showing that the costs of this lander are consistent with what a New Frontiers mission would be, which was not the answer in the previous decade. So all of these advances that have happened, including the changes in the costing, and especially the capability of the launch vehicle, have really enabled all of a sudden a mission like this to fall under New Frontiers. So I want to end that, groundbreaking science that can only be addressed by in situ measurements of the innermost planet is feasible and compelling for a New Frontiers class mission in the next decade. And that was a really exciting result here. And so, this is not the only lander that could ever be proposed. This is a representative lander that a science team could, tailor the payload of or the landing location of, but it really shows that you can do compelling science. That's the next step of studying Mercury in a New Frontiers cost cap. Thank you.
All right, thank you, Carolyn. We have a number of questions coming in. I'm going to skip over the first 2 because one of your team members looks like they've already answered them, so we can come back at the end if we have some time. But we'll start with, and I apologize, I'm going to totally mispronounce some of these last names. There's a question from Suniti Carolyn Tilaki at LSU. The question being, what in situ observations of variations in potassium and thorium abundances have you planned for insight into possible volatile-driven paleo-weathering processes or mantle evolution?
Well, we have, as you saw, and I can go back to a pretty robust payload to investigate the Mercury environment. So all of these instruments will be taking a look at the environment right above the surface through those 3 months. I am not a exosphere expert, so I don't have a great answer to what you exactly asked. But we can certainly.
Somebody has put in the spreadsheet that the gamma ray neutron spectrometer should be able to look at those variations.
Oh, perfect. So that's here too. So we will definitely get details of that into the answers on that Google Doc. But we do have a really robust suite of instruments that can address these.
Next question is from Bill McKinnon at Wash U. Did you consider landing near the poles to better manage the thermal load?
Yeah, we did. If you look at this figure here, especially at the north, there's not so much of this low reflectance material there. And so we had, large expanses of the low reflectance material at somewhat, mid-latitude areas where we could at least operate through the night, and a little bit on either side. And we were really compelled by that LRM. Of course, you could land somewhere else. You would have a lower chance of getting that LRM, but you could study directly the volcanic composition, or potentially even the polar deposits, of course, in the permanently shadowed craters. But we went with where we did away from the pole just because we wanted to go into this LRM.
Okay, next question is also from Bill McKinnon. What about the hollows? Any science progress there, or is that best left to Bepi?
So the hollows, for those of you that are not familiar, there are these kind of pit formations that were discovered by Messenger. They seem to be associated with the low reflectance material, which is again another reason to learn more about those. And one of the leading hypotheses of what they are is that it's loss of material in the rock, perhaps sublimation of something volatile in the rock that's then leaving a void. And so you could get, depending on if there are hollows where you're landing, you could get higher and higher resolution images from the descent imager. If you were super lucky, I guess you could get images with the panoramic imager or the foot cameras, but I would think that would be unlikely. But the most information you would get is really understanding what is the mineralogy of this low reflectance material, and then what does that mean for this sublimation or loss of volatile material hypothesis for the hollows. And then we also don't know, are hollows a formation that kind of has one diagnostic size, or do they get smaller and smaller if you were able to get higher and higher resolution images? So.
Okay, I'm just trying to keep up with the team members who are answering questions. Next one from Jim Cutts at JPL. Did you rule out the possibility of a mission that could survive the Mercury day and could provide long-term seismic observations?
Yes, we did not go with that. If Sanai or one of the other engineers wants to give more details on that, they can jump in after. But yeah, we went in with assuming that we would be going through the night to manage the thermal environment. Some team members were imagining different types of, crazy parachutes or tortoise shells or umbrellas that you could get to last a little bit longer. But the other thing is we really wanted to fit in the New Frontiers cost cap, and I think that would probably be something that would drive up the cost quite a bit. Sinai, did you want to add anything there? Okay.
All right. Let's see what hasn't been answered. Okay, Kyle Phillips at NASA Glenn. What type of ground tests do you anticipate? Have you identified the necessary facilities? If so, would you mind listing the anticipated test facilities or labs?
So this is just a mission concept study, and it's got a concept maturity level of 4. And so we did not go into a level of detail like that. If you were actually proposing this study, you would have to identify some of those things, but we didn't go into that level of detail.
Okay, next one, Melissa Battler, Mission Control Space Services. Have you considered autonomous operations during the 1 month without comms with Earth?
Yes, that's basically what we'll be doing. So we lose communication with the Earth, and those instruments that I listed will still be taking data over that time. So we'll have to, I guess, yeah, we'll have to program them to do that. I guess the question is really maybe more, would you adapt anything during that time if something happened in order to change a frequency or something like that? We didn't look into that for this study.
Okay, question from Zoltan Vaci from UNM. Will the mass specs be able to measure stable oxygen isotopes? I ask because there is potential for Mercury meteorites that exist on Earth.
I do not know the answer to that offhand. We can certainly ask the experts.
No, I think is the answer somebody has written, okay. And I would probably agree with them. Question from Jayadev Pradeep, ISRO. Wouldn't an orbiter and lander mission concept be more advantageous in the sense that the orbiter can possibly ensure communication of the lander with Earth at all times, as compared to the major break in communication that the lander alone would experience?
Yes, it sure would, but that would also drive up the price. And although we were not cutting things to get it to perfectly fit in that New Frontiers box, we were aiming at that level around there. So of course you could do more if you were trying to fit into more of a flagship cost, but having an orbital relay was just not going to happen in a near New Frontiers cost.
Okay, next one. Reed Sperling from University of Arizona. What steps can be taken to limit risk during the relatively long gap in communications with Earth?
Well, thermally, as long as you can test on the ground and be assured that you'll be fine through the cold, I think that's really the major question you would have as to can you survive. I think in terms of taking data, you would have to plan so that the spacecraft could autonomously come out of a safing event or something like that, and at minimum reestablish connections and hopefully start all of the data operations back up again by itself, since you completely have no knowledge of what's happening or no way to do anything in that period of time. And then the other thing is, of course, we'd prioritize the data downlink and the data acquisition up front, so that if for whatever reason you lost the lander during that night and could not reacquire the signal, you still get the valuable data to address the science objectives.
Okay, so that's all the questions that nobody's answered to. We've got a couple of minutes. I can ask some of the other ones just if you want to elaborate on what the others have written. So there's a question from Anthony Intravea. Is the landing area thought to face the solar wind? So somebody responded that you'll land around dusk and go through the night to dawn. Would you like to add anything to that?
No, but I guess if the solar wind is coming off of the sun, then it would probably be pretty grazing and then disappear through the night and then come back up as grazing.
And then question from Sean Su at CU Boulder. Would it be feasible to carry an impact ionization type dust detector, which will not only provide counts, but also more detailed info, including size, speed, and composition? And then somebody's written, we considered that, but mass, power, and cost were problems. In the next 15 years, perhaps other instruments will present themselves as viable options.
Yeah, that's pretty much it. The dust detector is relatively simple, and so it was something we put on there, and we do the payload that we used as kind of analogs to do this study. The great thing is that they're all at least a TRL-6. This is not early TRL-3 studies and stuff like that. These are things that are either going to fly or have flown, and so that makes a lot of this study and that portion of it really robust, because they exist and we have a good idea of what they cost and a good idea of how they operate. And so the dust detector we have on there has flown, and so we have a good idea of what it could do. But of course, in the time between now and when a Mercury Lander mission were to actually be proposed, there will be advances, and we could of course consider something more capable that perhaps would then be of low enough power, mass, and cost to put on there.
Okay, and just quickly as the final question from Anna Mittelholtz at UBC, could it be a possibility to also measure the electric field in combination with the magnetic field for electrical conductivity studies? And again, someone said, similar to the last one, problems with the mass and power, cost, etc. But again, could be a future instrument. Anything you'd like to add in the last 60 seconds?
No, but again, just to iterate that, it's exciting that we have, a high TRL payload that we could slap onto a lander right now, but there are tons of advances that are happening all the time in instrumentation that we would, of course, hope that the community would take advantage of when proposing a mission like this. And even beyond that, there are certainly instruments that we may have not considered or considered and decided against for the study that a different science team might prioritize or put on there. So there's lots of options. And this is just showing that the lander concept itself, with a robust science payload addressing really important science goals, is something that you could fit in the New Frontiers cost cap.